Okay, hi, welcome back. So we will just go where we left off. I'll just need to cancel off this h. Okay, we were talking about the order of magnitude for del t del x, then del t del y. Okay, and this will be basically all the terms in front over here. All of these things are on the order of magnitude of 1, which will describe the shape of the profile, the dimensionless temperature profile. Okay, within the thermal boundary layer. So I'll just cancel these two off. Okay, I'll just cancel these two off, and I will have it as such. Now, basically, what this is saying is that I can just log all the coefficients off. I can take all the coefficients off, and basically we'll just have a fully non-dimensionalized equation here. Okay. So I have a V star. I can take this off and I have a U star. Okay, so oh shucks, did I just delete the wrong terms? I think I did. Okay. Okay, never mind. I will just paste this here. Okay. So now at least we have a non-dimensionalized version of our equation. It will be slightly easier to see what our temperature profile is like. So instead of having a T versus X or T versus Y temperature profile, we can actually have a so-called how do you say? Okay, you can have a so-called what do you call that? Yeah, you can have a temperature profile. Yeah, based just you don't have all the scaling factors there. It's all non-dimensionalized, so you can just take a look at the shape. Now, how do you actually so-called deduce a temperature profile from this? Okay, so yeah, we'll have to hold y constant. Okay, because we are looking at the temperature profile across the x-axis, we'll hold y constant. So for this, we'll hold y constant, and let me yeah, just ignore all of this. This was just all the stuff I was talking about earlier. Okay, we need to assume a shape of the velocity and temperature profile before we do the integral curve analysis. Okay. Okay, so yeah, let's take a look at each of these terms so that we can see what's the contribution. Okay, so this is the conduction term. So let's take a look. Okay, or rather, okay, let's do it the easier way, right? So we have a downward sloping temperature profile from here. T going down, maybe linearly, maybe exponentially, I don't really know. How do we know what is the shape? So if it was an exponential curve, what will we expect? Okay, usually exponential equations, they look like this. Okay, del t dx equals to minus k of t. Okay, so what happens is that t will be brought to the other side. We have a logarithm, and then we'll have t equals to some t naught exponential minus kt. Alright, or kx, sorry. okay, minus kx. Okay, so usually in exponential curve or whatever, we will have this sort of equation. Okay, if we take a different derivative of this, okay, so we have a d2t dx squared. Okay, so what happens? We'll just have k dt dx. Okay, so this is what if it's an exponential curve, this is what the equation will look like. Okay, d2t dx squared equals to some constant in front times dt dx. Now what do we notice here? We have this u star, which when we hold y constant, u star is sort of constant-ish. Okay, I won't say it's constant, but it's somewhere there, right? It's constant-ish. There's some constant in front here. There's del theta del x star, the non-dimensional temperature gradient, and then this will be equal to the del 2 theta del x star squared. Okay, so this kind of gives you a clue as to what this equation looks like. Okay, what this equation looks like. Okay, then that gives us a clue as to what this part looks like. It may be a sort of exponential equation. Now, of course, u is negative. U is negative. Why is u negative? Because if we take a look at this diagram, x goes in the right direction, but likely velocity of fluid will flow from the cold part of the region to the hot part of the region as part of natural convection. So u should always be negative. Okay, it should be less than 0, or at least u star should be negative. So from this we can see some sort of rationale for exponential decay curve. Okay, so this is one way of thinking about it. And of course, the question is, what about this term here? What about this term here? This term is not exactly dependent on x, and it's not exactly constant, but it's okay. It's on an order of magnitude of 1, which is fine. Same as this, but what will this then do? Okay, what will this then do? Okay, okay, we don't really know. Okay, we don't really know. But yeah, basically we can think of it this way. Okay, if you have your what do you call that, control volume here. You have a thermal heat flux flowing from the wall. So this is Q double prime. This is conduction. Okay. So I'm ignoring this term here. I will only look at this term. Okay, so this is the dt dx term. So this is how Q double prime will scale. So this will be at x, and what is leaving is at t dx x plus dx. Okay, so good thing over here we will have a v star term. Okay, v star is all on this side, top and bottom. Okay, all the terms are over here, so it makes it nice to read on the diagram. So what is this term describing here? Okay, this actually describes, you know, basically what the advection. Okay, there will be advection, so there will be some, physically speaking, there will be some fluid entering the bottom and some fluid leaving the top. Maybe, yeah, I'll just use this v star or v. Okay, so it will come in at some temperature T at y and some temperature Ty plus, T at y plus dy. Okay, now what will we have here? Okay, we will have this term here, Ty plus dy equals to T of the box. Okay, T of the control volume. Okay, so we assume the control volume here has just one uniform temperature. That's how we can all think of it differentially speaking. This thing here will be cooler. Okay, it will not be the same as the control volume temperature, but likely it will be cooler. Okay, it will be some function of y or whatever, I don't know. Okay, why is it cooler? Okay, if you have your boundary layer, if you take a random piece of a block here, notice that the cool fluid actually flows from the bottom. Okay, the cool fluid actually flows from the bottom. Okay, with the fluid equals to T infinity. It will flow from the bottom, it will contact the wall, it will get hotter as it goes up. So this Ty will be cooler. It's a cooler. Alright, a cooler effect. Okay, so what does this mean? Okay, if we were to write all this out, yeah. If we were to just to write the energy balance equation, what's going in? Okay, dt dx at x. What's going out? It's a minus. So this is the conduction part. Okay, I'm not writing all the terms so-called neatly and all that, because yeah, I didn't write the conductivity, and I didn't write conductivity and anything like that. Okay, so this length here is dx. If you want to write it in a non-dimensional version, that's even better, because that will actually save us a lot of hassle. But I won't bother doing it. But it's more or less the same pattern if you think of it in a non-dimensional sense. Okay, because you don't have to think of alpha or anything else. Right? So that's what this term here is. This is the Laplacian term. Okay, this is the Laplacian term, and then what's coming in? Okay, what's coming in is maybe okay, vty, okay, plus vty minus vt of the control volume, right? So this is vt of the control volume, and what do we have here? Okay, so this is the picture, and this is the equation that just comes about. I'll just delete all of this. Okay, I'll delete all of this, and I'll just say that this term here actually just corresponds to d2 theta over dx star. Okay, and this thing you of course have to do a 1 over delta y, of course, blah blah blah. And that will be the stuff on the right. Okay, it will have one term, maybe 1 over delta y star. Okay, minus v times theta, or v star, sorry, v star. Maybe I should just put the v star on the outside. V star. Okay, minus TCV, or theta CV plus theta at y. I mean, just outside the box, just at the bottom of the box. Okay. All right. So okay, if we make the limits very small, I mean, this after all here is actually theta CV. This is theta CV. This is something quite out of control, is some function of y. Okay, I don't know what it is, but you see, you have again a very similar pattern here. This is a d2 theta kind of a term. This is a minus theta kind of a term. Okay. So again, we'll have this same pattern, d2 theta. I'm not going to write the by the ax square or whatever, equals to minus k theta. Now what is this? This is a simple harmonic oscillator kind of equation, but just as well, it actually fits the exponential sort of equation. The exponential so-called decay curve also works here. All right, the exponential decay curve actually works pretty well here. This thing is actually a function of y. It has nothing to do with x. So if y is constant, this thing can be treated as a constant, right? This thing can be treated as a constant. Okay, so if this is a constant, this is a constant. Because this one actually changes with x, I don't really know how. Okay, but well, yeah, we don't know how the velocity profile actually changes with x yet, but at least if we just hold this constant, okay, just in a hand wavy way, we can actually see that this also looks like an exponential sort of equation pattern. Okay, this is an exponential decay kind of a pattern. Okay, so hopefully that's convincing enough that you will know that, you know, exponential yeah, using exponential decay isn't too far off an idea. So the actual profiles that are being suggested in Bijan's textbook, it is exponential decay. So I just wanted to really convince myself of that. That's why I did this whole exercise. Okay, see whether it's actually viable. And now there are actually two parts here. Okay, one is, of course, it's dependent on x, as I was describing earlier. The other part, it's also dependent on the thermal boundary layer thickness. This is where the y dependence so-called comes in. Okay, so this is where the y dependence comes in. Okay. So now for high Prandtl number fluids, if we know this, we assume this sort of temperature profile or dimensionless temperature profile, we can take a look at back up here, and if we substitute this dimensionless so-called dimensionless temperature profile back in here, we would know that this vstar should be also in sort of an exponential curve as well. Okay. Again, I say if we substitute theta back into our boundary layer equation, okay, for the fluid bit, okay, we should know that this v if we substitute theta in here as no, okay, never mind. I'll just copy. Where's the thing? Yeah, let's substitute back into our boundary layer for high Prandtl number fluids. Yeah. Okay, so now if we have sort of derived this, theta is sort of an exponential thing. We have sort of seen from the differential equations how we can convince ourselves of that. Okay, it's exponential minus x plus some constant value which is dependent on y. Okay, if we were to substitute this back, okay, I know the proof is not as rigorous, but at least it should give you some clue as to why exponential profile is okay. Okay, if we don't have any experiments at all, it's a good first guess. Okay, so if we want to substitute this back into this equation here, if we were to substitute back into this equation here and we just take out this parental number term, this is what we'll get, and we can see that the velocity profile should also follow more or less an exponential profile. Okay, when we hold the y constant, when we hold y to be constant, the Rayleigh number at h will be constant. This ratio should also be constant with y because this whole term here is on the order of magnitude of 1. So yeah, actually let me just make it clear. So this should be on the order of magnitude of 1 times this exponential term. So now we see that this v star, okay, v star is equals to some function of exponential minus x over delta t. So we know that this is a function. We can just do some simple integration, and of course you want to you put this dimensionless version here, that's fine as well. Yeah, I'm just doing it in a very quick and rough way to give you intuition. So the actual profile given here is this. Okay, the actual profile given here is this. Okay, we sort of established that for temperature versus x, we have exponential decay. Then for velocity, we have this sort of shape. Okay, because you have a no slip at the wall, it will go to some maximum and then it will start dropping off again. Where this drop off happens, I don't really know, but remember the boundary layer thickness here will be thicker than here. Okay, that's the main thing we want to have. Okay, so how does this work? Okay, so there will be exponential increase. Okay, exponential increase in boundary layer thickness, or in v. So this is v. So there'll be increase in v, but then it'll start to drop off. Where does it drop off? It will start dropping off once the thermal boundary layer ends. Okay, and we already had a clue before. So this v star should be some function of this exponential decay curve thingy. So we can just differentiate this twice, and then based on this equation, we can see that v star will be some negative exponential of x over delta t, or x star over delta t, whichever you want. Okay, what is the other stuff that's in there? Okay, okay, so since this actually accounts for the exponential decay, we need something to account for this exponential increase part, because we already accounted for this shape, and this shape actually follows this thermal boundary layer shape. Okay, at least within the thermal boundary layer, it follows this. Yeah, that's a more accurate way. So how do we describe this? How do you describe this? Okay, so so this will be described by this term over here. There's some exponential increase. Exponential increase in what do you call that? Yeah, exponential increase in velocity. Of course, there'll be some vy that's a function of y, and this, okay, this is the answer. So, okay, let me do some addition. So these are the textbook answers. Okay, so hopefully this will help you to excuse me, sorry, I didn't intend that, but okay. Yeah, anyway, so anyway, this is how we get our estimated velocity profiles. Okay, if you really want a little bit more to convince yourself a little bit more. Okay, I have a qualitative explanation over here which you can read in your own time. Hopefully the math that is done in this videos should help you to be convinced of what sort of profiles we want to substitute into our equation. Okay, so we have not even solved the integral solution yet, and we probably need to do that more in the next video. So yeah, stay tuned. Okay, so yeah, remember integral solution, we have to integrate everything across the whole boundary layer. I'm not going to do the control volume version, but I'll stop now. I'll continue more next time. Okay, see you.